welcome to Talk Tensors.
Oh.
So I want you to look around the room you are sitting in right now. Like, take a second to really just observe it.
Yeah, maybe you are in your living room or sitting at a desk in an office.
Right, or maybe you are listening to this on a commute. But wherever you are, you understand intuitively that the things around you, like say the coffee table in front of you, has actual physical volume.
Exactly. It occupies physical space between you and the sofa.
Yeah, you understand the depth of the room. You just know that to pick up a mug from that table and, put it in the sink, you have to reach forward, close your hand around a three-dimensional cylinder, lift it, and navigate around a chair.
And you don't even think about it. It is just instinct.
Completely automatic. But for an artificial intelligence, that kind of spatial reasoning has just been this impenetrable wall.
Oh, absolutely. It is a massive hurdle.
So today, we are doing a deep dive into a groundbreaking piece of research that details a new architecture called LO. That is an embodied, multimodal generalist agent.
It is a fascinating paper.
It really is. We are going to explore how this research takes the immense reasoning power of large language models, like the ones powering text chatbots, and pulls them off the flat 2D screen.
Right, plunging them directly into the 3D physical world.
Exactly. To perceive, ground, reason, plan, and act, all using a single unified architecture.
And I just want to say, the ambition of this thesis cannot be overstated. I mean, we have spent the last decade building these brilliant systems that are essentially trapped behind glass.
Trapped behind glass. Yeah, that is a great way to put it.
Right, because they are spectacular at language generation, and they can paint these award-winning digital pictures.
And analyze two-dimensional photographs with superhuman accuracy.
Exactly, but they completely lack the fundamental spatial comprehension of the physical world that biological organisms just take for granted.
Because they have never actually lived in it.
Right. And this research, it isn't just proposing a robot that can walk or, a software program that can label a 3D architectural scan.
It's much bigger than that.
It is proposing a singular mathematical brain that does it all. One model that is capable of answering complex linguistic questions about a room's layout, planning a sequential physical task, and then directly outputting the precise motor commands to steer a robotic arm to execute that task.
Which is a massive paradigm shift, because if you look at the historical context laid out in the research, we have seen an absolute explosion of foundation models recently.
Well, totally. Massive language models acting as general-purpose problem solvers for text.
Right. And we have also seen the rise of vision language action models, or VLA models.
The paper specifically examines architectures like RT1, RT2, Gato, and Polemi.
Yeah, and those models have shown massive success in robotics, right?
Yeah.
Taking web-scale knowledge and transferring it to robotic control.
They have. They are incredibly impressive.
So the natural question for you, the listener, is probably, well, if these models already exist and are already moving robot arms, what is the fundamental problem LEO is actually trying to solve?
And the problem is what the researchers characterize as the limitation of 2D domains.
The 2D domain limitation.
Yeah.
Unpack that for us.
Well, almost all of these existing generalist models, no matter how advanced their language processing is, they interact with the physical world through the flat lens of a 2D camera feed.
Right, they're just looking at flat video.
Exactly. They process grids of pixels. But human-level intelligence, and frankly, even basic animal intelligence, is entirely enveloped in a 3D physical environment.
We don't just see colored pixels. We perceive volume and distance.
And occlusion and spatial relationships, right.
Mm-hmm.
The researchers argue that this reliance on 2D images is a severe bottleneck.
Because it stops them from understanding the real world.
Exactly. It prevents current models from truly solving real-world tasks and approaching general intelligence, simply because they rarely explore tasks inherently defined in the 3D world.
Like 3D grounding or embodied physical acting.
Precisely.
I always try to conceptualize this using an analogy. So imagine you have a brilliant scholar. This person is an absolute genius, like a polymath who has memorized every encyclopedia ever written.
Okay, I like where this is going.
But this scholar has lived their entire life locked inside a movie theater. They have only ever seen the world projected onto a flat, two-dimensional silver screen.
Right. A total 2D existence.
Yeah. So they know all the facts about the world. They can describe the aerodynamic properties of a car. They can detail the architectural style of a house, but they have never actually walked around a physical car.
They don't have that geometric intuition.
Exactly. They don't intuitively grasp that a car has a back bumper that you cannot see from the front grille, or that you have to physically walk around a solid sofa to get to the television?
Because a 2D screen doesn't require you to move around things.
Exactly. So if we look at a model like RT2, which is already doing robotics using 2D cameras, what specific mechanical gap does a fully 3D aware agent fill that a 2D camera feed just fundamentally misses?
It really comes down to the mathematics of geometry and spatial relations. I mean, a 2D camera feed can show a robot a picture of a coffee table and a bed. But understanding the physical volume of those objects, like knowing that if the bed is between the robot and the coffee table, the robot cannot just walk in a straight line to get there, that requires true 3D comprehension.
Because in a 2D image, things just overlap.
Right. Objects overlap, and scale is highly ambiguous depending on the lens and the focal length you're using. Depth is really just an algorithmic guess.
So to actually do anything physical, you need more than a guess.
Exactly. To effectively plan a route or manipulate a physical object, an agent needs an object-centric global view of the space. It needs to know the exact X, Y, and Z coordinates of every bounding box in the room.
And a flat image just can't give you reliable X, Y, and Z coordinates.
Right. Think about a robot arm trying to grasp a transparent glass cup. A 2D camera might completely fail to see the edge of the glass because of the lighting and reflection.
Oh yeah, the camera just sees right through it.
Exactly. But a 3D sensor capturing the spatial geometry knows the cup occupies a specific volume of space regardless of reflection.
Wow, yeah. That is the barrier we have been hitting.
And crossing it requires entirely rethinking how an AI ingests sensory data.
You can't just feed it a flat photograph anymore. You have to somehow build a 3D brain.
And that leads us to the architecture of LEO, which is just incredibly elegant.
It is elegant, but it is also technically dense. I mean, they built a system that handles multiple radically different types of inputs simultaneously.
Yes, 3 main inputs.
Right. First, it takes in egocentric 2D images. That is the agent's eyes, basically. What it sees right in front of its camera lens from a first-person perspective.
That is the first stream, yes.
Second, it takes in global 3D point clouds. This is an object-centric overview of the entire room.
Almost like a LiDAR scan of the whole environment.
Exactly. And third, it takes in textual instructions from a human user.
And from those 3 completely disparate inputs, it outputs both text responses, like a conversational chatbot, and continuous physical action commands for a robotic system.
Which is wild.
Yep.
And the engine processing all of this is a large language model.
Yes. Specifically, the researchers utilize Vicuna 7B as the core LLM.
Right. Yeah. Now, adapting a text-based brain to understand 3D point clouds and robotic joints without, destroying all the massive linguistic knowledge it already learned during its original pre-training, that is a delicate operation.
Extremely delicate. If you mess that up, the model forgets how to speak English.
Exactly. So they use a technique called LoRA, which stands for low-rank adaptation.
Yes.
I want to pause on LoRA for a second because it is such a vital concept in modern machine learning. When you take a model with 7 billion parameters, like Vicuna 7B, you don't want to retrain the whole thing from scratch.
No, it would take a massive cluster of GPUs and millions of dollars.
Right. So how does LoRA actually allow them to bolt these new 3D senses onto the model without inducing catastrophic forgetting?
The mechanism of LoRA is really fascinating. So instead of updating the original 7 billion weights of the neural network, you freeze them.
You just lock them down.
You make them completely read-only. Then you inject small, trainable rank decomposition matrices into the layers of the transformer architecture.
Okay, that sounds super technical. Can we break that down?
Sure. Think of the frozen original model as a massive, heavy encyclopedia that you are absolutely not allowed to write in.
Okay, an untouchable encyclopedia.
Right. LoRA leaves essentially a series of transparent sticky notes placed over the pages.
Oh, I love that analogy.
Yeah. You write your new specialized knowledge, in this case, how to interpret 3D data and output robotic actions on those transparent sticky notes.
So during a calculation, the model reads both at the same time.
Exactly. It reads the original frozen text and the modifications on the sticky note simultaneously. Out of the 7 billion parameters in Vicuna 7B, the researchers only actually tune about 142 million of them.
Wow, just 142 million. That is a tiny fraction.
Right, which makes the training process incredibly efficient while perfectly preserving the model's vast common sense reasoning capabilities.
Okay, I love that sticky note analogy.
Yeah.
But here is where my mind really starts to bend with this paper.
Okay, Kimmy.
How do you feed a 3D point cloud, which is just a massive array of spatial coordinates, into a text-based language model?
It does sound contradictory, doesn't it?
It sounds like trying to force a square peg into a round hole. I mean, a language model expects words. It expects letters.
The solution they came up with is tokenization. They turn everything, and I mean everything, into a single, unified sequence of tokens.
So the text, the 2D images, the 3D shapes.
And even the robotic movements, it all becomes tokens.
Right, and a token is just a fundamental unit of meaning.
Exactly. To the LLM, it doesn't matter if the token represents the word apple or a patch of green pixels or a specific 3D shape in the corner of a room. It is all just numerical vocabulary to the model.
Okay, let's break down that tokenization process mechanically because I want to make sure we get this. Let's start with the easy stuff.
Text.
Right, text. For the text instructions, they use a sentence piece tokenizer,
which breaks human language down into a vocabulary of about 32,000 subwords.
Okay, so the word unbelievable might be broken into unbelieve and able, and each piece gets assigned a specific token number.
Simple enough. Then, for the 2D images, they run the visual data through an OpenCL-like convex encoder. How does that translate an image into tokens?
Well, a convex encoder is a highly modernized convolutional neural network. It looks at the 2D image and processes it through hierarchical layers.
To understand the fine details.
Yes, like edges and textures. But also the high-level semantic meaning, like recognizing that a collection of textures is actually a dog or a chair.
And then it compresses that.
Exactly. It compresses that rich visual information into a sequence of dense numerical vectors, which are then linearly projected into the exact same mathematical dimension as the text tokens.
Oh, so the language model can basically just read the image patches like it reads those subwords.
That is exactly what happened.
Okay, so text becomes tokens, 2D images become tokens, but the 3D data is completely different geometry. It is an object-centric point cloud.
It is a lot more complex, yeah.
How do you tokenize the physical shape and location of, say, a sofa? This requires a highly specialized pipeline. The 3D input isn't just a random scattering of points in space. It is actually segmented into individual objects first.
Okay, so it separates the sofa from the floor.
Right. And then they use a pre-trained point cloud encoder called PointNet++ to process the 3D shape of each individual object.
PointNet++ weak. Why use that specifically?
It is brilliant because it is designed to consume an unordered set of points in 3D space. It hierarchically groups these points into local regions, extracts features from those regions, and then aggregates them.
So it builds a mathematical summary of the shape.
Exactly. It gives you a mathematical embedding that describes the geometry of the sofa, its shape, its curvature, its physical volume.
But wait, knowing the isolated shape of a single sofa isn't enough, right?
Not if you want to understand a room, no.
Right. Because if the model is going to navigate a room, it needs to know how that sofa relates to the coffee table, the television, and the walls.
Precisely. Which is why they don't stop at PointNet++.
What happens next?
They take all those individual object embeddings and they pass them through a module called a spatial transformer.
A spatial transformer, okay.
This is where the 3D comprehension truly happens. So a standard transformer attention mechanism, which is the core tech behind all LLMs, looks at a sequence of tokens and figures out which ones are relevant to each other.
Like in a sentence.
Right. In a sentence, the word bank pays attention to the word river to know it means a river bank, not a financial institution.
Okay, I follow that.
The spatial transformer modifies this attention mechanism. It biases the mathematical attention weights based on the relative physical positions and sizes of the objects in the 3D space.
Wait, how does an attention mechanism actually get biased by spatial data? I really want to make sure we don't gloss over this, because this sounds like the crux of how the AI understands physics.
It is literally the mathematical heart of the system. So in standard self-attention, you have queries, keys, and values.
Right.
The network computes a dot product between the query of one token and the key of another to determine their relationship score.
Basically asking how important are these two things to each other.
Exactly. Now, in the spatial transformer, they inject explicit 3D positional encodings directly into this calculation.
How?
They take the bounding box of object A and the bounding box of object B. They calculate the 3D distance between their centers, their relative orientations, and their relative volumes.
Oh, wow.
Yeah, and this geometric data is passed through a multi-layer perceptron to create a spatial relation feature. And that feature is then added directly to the attention matrix.
Oh, I see. So the network mathematically forces objects that are physically closer to each other in the X, Y, and Z coordinates to pay more attention to each other than objects that are all the way across the room.
That is exactly right.
So like if a mug is sitting directly on top of a table, the spatial bias ensures their attention weights are deeply intertwined, so the model understands they are physically interacting.
Exactly. And all of that spatially aware data is flattened into a sequence of 3D tokens.
That is incredible.
So when you prompt the Vicuna LLM, the input sequence literally looks like a string of text tokens representing your instructions, followed by a string of 2D image tokens representing the camera feed, followed by a string of 3D object tokens representing the layout of the room.
And the LLM just processes them all simultaneously in a single forward pass.
Just reads them all at once.
Okay, but wait. We haven't even touched on the most mind-bending part of this entire architecture.
The action outputs.
Yes. We've talked about the inputs, but how does a language model output a physical movement?
It is wild to think about.
It really is. Like, how does an autoregressive text generator move a robotic arm?
This is perhaps the most elegant engineering choice in the entire paper, in my opinion. For embodied tasks, the agent needs to output continuous physical actions.
Right.
If you want a robot arm to pick up a cup, you have to tell its motors to move to specific continuous coordinates along the X, Y, and Z axes, and you have to specify the continuous rotation of its wrist joints.
You can't just give it a vague text command. It needs hard numbers.
Right. So the researchers took those continuous mathematical actions and they discretized them. They broke them down into specific rigid bins or steps.
So instead of saying, move the arm exactly 0.543 meters forward, you create a bin that represents move forward by a tiny increment.
Yes.
And another bin for the next increment.
Correct. They quantized the continuous action space into a finite number of discrete bins, and then they mapped those discrete physical bins to the least used language tokens in the sentence piece vocabulary.
I am hung up on this concept because it is so incredibly clever.
It is brilliant.
I mean, the sentence piece vocabulary has 32,000 text tokens. Most of them are common words or syllables.
But there are hundreds of highly obscure tokens.
Exactly. Maybe strange Unicode characters or obscure foreign language prefixes that the model almost never uses during normal conversation.
Right.
And the researchers just find these obscure tokens, let's say token number 31,999 lines, and they just assign a totally new meaning to it.
They completely reprogram it.
They say, okay, whenever the model outputs token 31,999, it no longer means some obscure suffix. It now means move the robot arm forward along the x-axis by one discrete bin.
That is the exact mechanism. They allocated specific unused tokens for navigation commands. Move forward, turn right, turn left, stop.
And for the arms.
For manipulation tasks, they allocated 516 obscure tokens just to discretize action poses. They dedicated 256 tokens to represent the X and Y axes on a grid, and other tokens for Z rotation and arm extension.
But why do it this way, though? Like, why hijack obscure text tokens instead of just expanding the vocabulary and adding brand new dedicated action tokens to the model?
That is a great question, because expanding the vocabulary of a pre-trained LLM is mathematically disruptive.
Oh, it messes with the original training.
Exactly. If you add new tokens, you have to expand the model's foundational embedding matrix. The new tokens start with randomized untrained weights.
Which means the model has to learn how to use them from absolute scratch.
Right, which takes massive amounts of training data and compute. But by repurposing the least used existing tokens, you leverage the fact that those tokens already have established stable positions within the model's high-dimensional embedding space.
Oh, wow.
The model already knows how to process them. You are just teaching it to associate them with physical actions instead of obscure text concepts via the LoRA fine-tuning.
The elegance of that is just staggering. The AI is literally reading the 3D room, and it is speaking robot movements using the exact same autoregressive text generation mechanism it uses to write a summary of a document.
It just predicts the next logical token.
That is amazing.
The beauty is the unified objective. By formulating everything as a GPT-style autoregressive prefix language model, you completely eliminate the need for separate isolated brains.
Right. You don't have one neural network architecture for computer vision.
And a different architecture for parsing speech.
And a third, entirely separate control policy network for motor movement.
Exactly. The LLM simply looks at the context of the previous tokens and predicts the next token in the sequence.
So if the context suggests the user wants a question answered, the next token is a word.
And if the context suggests the user wants the room cleaned, the next token is a command to turn a steering wheel.
That is phenomenal. But, this is a massive but.
There's always a but.
Always. Having a unified brain is only half the battle. You can build the most elegant, mathematically perfect architecture in the world, but a machine learning model is really only an empty vessel.
It is only as good as the data it learns from.
Exactly. And this brings us to a profound roadblock the researchers hit: the data bottleneck.
This is a critical issue in the field right now.
Yeah, because the secret sauce behind the immense success of models like GPT-4 or standard 2D image generators is the sheer, unfathomable volumes of training data.
They are trained on internet-scale datasets. We are talking about billions of text documents scraped from websites.
And massive datasets like LAON5B, which has billions of 2D image text pairs scraped from the web.
Right. You just run a web trawler, download an image, grab its alt text, and you have training data.
Right. It's relatively easy to acquire 2D data because humans have spent the last 30 years uploading 2D photos to the internet.
Exactly. But large-scale 3D training data,
It doesn't exist.
it essentially does not exist at that scale. You cannot just scrape the internet for millions of richly annotated interactive 3D rooms.
Right. Gathering 3D data requires physical LiDAR scanning of actual environments.
And even if you have the scans, manually labeling every single object in a 3D scan with its exact spatial coordinates, its color, its material, and its geometric relationship to every other object in the room, that is incredibly costly and time-consuming.
You would need an absolute army of human annotators.
Which is why advancement in 3D scene-level understanding has severely lagged behind 2D vision. It is this exact bottleneck.
So you have built this incredibly powerful 3D brain, Vicuna 7B, augmented with LoRA and spatial transformers.
Right.
But the textbook you need to teach it about the 3D world hasn't been written yet. So how did the researchers solve this?
They had to write the textbook themselves.
And they did it using a two-stage learning scheme, right? 3D vision language alignment, followed by 3D vision language action instruction tuning.
Yes.
And to generate the massive amount of data needed for this, they built an LLM-assisted pipeline. I mean, they literally used an existing language model to generate the synthetic data needed to train their new 3D model.
It is a brilliant workaround to the human annotation bottleneck.
Okay, walk us through it.
So they created two massive synthetic data sets called LEO-align and LO-instruct. To do this without human labelers, they leveraged the reasoning capabilities of an existing powerful LLM, like GPT-4.
The teacher model.
Exactly, the teacher model. And they fed this teacher LLM what they call scene graphs.
And I think we need to unpack what a scene graph actually is. When you say they feed an LLM a scene graph, what does that payload actually look like to the computer?
A scene graph is a highly structured text document, typically formatted in JSON, that mathematically describes a 3D room. It is a graph of nodes and edges. The nodes represent every physical entity in the room, assigning each a class label and a unique ID. For example, sofa 1, printer 30, or window 5.
So it is just text saying what is in the room.
And more. The JSON payload lists the attributes of the object, like its color, its physical state, and its exact 3D bounding box coordinates.
Okay, so that is the nodes. What about the edges?
Crucially, the edges of the graph represent spatial relations. The document will explicitly state in text format. Sofa 1 is to the right of chair 2, or sofa 1 is inside room 4.
So they feed this massive JSON text array to the teacher LLM and prompt it, essentially saying, hey, pretend you're standing in this room. Generate thousands of realistic questions, answers, and dialogue interactions about this space.
Exactly. And the teacher LLM reads the JSON, realizes structurally that there is a red sofa next to a table, and generates a training dialogue.
Like, user, where is the red sofa located? Assistant, it is to the right of the second chair and directly in front of the table.
That is the generative process, yes.
And there's a big but here.
Here it comes.
If you have ever used an LLM, you know they have a fatal inherent flaw, which is hallucination.
Yes. They do.
They are statistical prediction engines, which means they really like to make things up if it sounds statistically plausible.
Right. If you ask an LLM about a living room scene, it might confidently generate a dialogue stating there is a television on the wall.
Just because televisions are highly correlated with living rooms in its pre-training data.
Exactly, even if the JSON scene graph never mentioned a television.
Right. And if you train LLA on hallucinated data, the resulting model will be completely untethered from reality. It will be useless for physical robotics.
Because it will be looking for things that aren't there.
I am so glad you brought that up, because that was my immediate skepticism when I was reading the methodology. I was really hung up on this teacher LLM concept.
It is a valid concern.
Because if we are using an LLM to generate the training data, aren't we just poisoning the well with hallucinations? Like a bad game of telephone where the teacher passes down its own delusions to the student model. How did they stop the AI from teaching LEO things that don't exist?
The researchers were acutely aware of this contamination risk, and they introduced a highly critical prompting strategy called OCOT.
Which stands for Object-Centric Chain of Thought.
Yes.
Now, chain of thought prompting usually means telling the AI to think step by step. How does OCOT work in practice with these scene graphs?
It forces the teacher LLM to explicitly show its mathematical work before it is allowed to answer a user's generated question.
Show its work how?
Well, specifically, the LLM prompt is engineered so that the model must explicitly output the exact object label and the unique numerical ID from the JSON file as an internal thought before generating the final conversational response.
Oh, I see. So if the generated training dialogue has the user asking, "Can you help me print a document?" the teacher LLM cannot just statistically predict, sure, there is a printer.
Right, it can't just guess.
It has to output a hidden line of text that says, thought, printer 30. It has to identify the specific node in the scene graph.
Exactly. And only then can it output the conversational response, sure, there is a printer on the desk.
That is so smart. By forcing the model to explicitly ground its reasoning in the specific IDs of the scene graph, it anchors the language generation to the rigid reality of the 3D data.
Precisely the mechanism. It breaks the statistical habit of hallucinating plausible but fake objects.
But they didn't rely on OCOT alone, right?
No, they didn't. They implemented rigorous automated refinement procedures post-generation. They used regular expression matching, which is a computational way to search text for specific rigid patterns alongside scene graph retrieval.
So they double-checked the AI's homework.
Thoroughly. A script scanned every single generated dialogue and strictly verified that every single object ID that AI mentioned actually existed in the original JSON file.
And if it hallucinated an ID?
If the LLM generated a sentence expressing uncertainty or mentioned an object ID that wasn't there, the entire dialogue was flagged and filtered completely out of the training set.
Incredible. And the methodology also mentions they ran into a really interesting and frankly kind of funny psychological quirk during training that required what they called data balancing.
Oh, yes. The yes ma'am problem.
Right. They noticed that the agent basically became a yes man. If you ask the early version of LEO, is there a rhinoceros in the bedroom? It would just say yes.
Why did it do that?
Well, why did it?
It is a classic machine learning pitfall related to dataset distribution. You see, when the LLM was generating the training questions based on the scene graph, it naturally generated questions about objects that were actually in the room.
Because humans rarely ask questions about things that aren't there. We don't walk into a kitchen and ask, is there a submarine in here?
Right, exactly. So the vast majority of the training questions asking, is there a stellier, were followed by the answer, yes.
And neural networks are lazy.
Very lazy. The model learns the statistical distribution of the answers rather than actually reasoning about the physical scene. It essentially learns the shortcut. If a user asks about an object's existence, the safest bet is just to say yes.
So how do you break a neural network out of being a yes man?
You have to artificially force it to say no.
Okay, how?
The researchers had to intentionally inject augmented negative samples into the training data.
Negative samples?
Yes. They systematically generated questions querying completely non-existent objects, forcing the model to learn how to scan the 3D point cloud, fail to find the object, and confidently say no.
Oh, that makes sense.
And they noted in the paper that this data balancing drastically improved the accuracy and effectively mitigated the hallucination problem on the agent's end. The exact match accuracy on object existence questions shot up significantly once the dataset was balanced.
Wow. Okay, let's synthesize where we are, because we've covered a lot.
We really have.
They have built this incredibly elegant, unified architecture using Vicuna 7B, LoRA, and spatial transformers to process text, 2D images, and 3D point clouds.
Right.
They solve the action output problem by discretizing robotic movements into obscure language tokens.
Yes.
And they bypass the human data bottleneck by generating high-quality, hallucination-free synthetic 3D data using scene graphs and OCOT prompting.
You've got it perfectly.
They have aligned the vision and language, and they have instruction tuned it for physical actions. Now comes the moment of truth. How did LEO actually perform when they put it to the test against the benchmarks?
The empirical results are remarkably strong. I mean, the researchers didn't just test it on one niche task. They evaluated LEO across a diverse spectrum of 3D benchmarks to prove its generalist capabilities.
What kind of benchmarks?
We are talking about 3D captioning, where it has to accurately describe complex objects or entire room layouts,
Okay.
3D question answering, and situated QA, which is much harder because the agent is asked questions based on a specific position and orientation within the room.
So it has to understand its own egocentric viewpoint relative to the global space.
Exactly. And they also tested it on embodied navigation moving through the space and robotic manipulation.
Let's talk about the state-of-the-art results. The paper highlights that LEO surpassed previous task-specific models on most of the vision language tasks.
Which is huge.
It is. I want to make sure the gravity of that is clear to the listener. Usually in machine learning, a specialist beats a generalist.
Almost always.
Right. A highly optimized model trained only to do 3D question answering with an architecture custom built for that one task will almost always beat a generalist model trained to do 50 different things.
The jack of all trades, master of none rule.
Exactly. That rule usually applies to AI. But LEO, despite being a multimodal generalist, actually set new state-of-the-art records on several benchmarks.
And that performance speaks directly to the power of the unified architecture. By forcing the model to learn multiple modalities simultaneously, vision, language, and 3D space, the representations inside the neural network become richer and more robust.
The knowledge transfers across domains.
Exactly. But what is even more impressive than the raw benchmark scores are the task planning and dialogue capabilities. Because LEO is an LLM at its core, it doesn't just output rigid binary answers.
Right. It can engage in scene-grounded common sense reasoning.
Yes.
There is a specific example in the paper that just blew my mind because of how human-like the reasoning is.
The bedroom example.
Yes. A user gives a highly ambiguous high-level command. Organize and tidy up the bedroom.
Right.
Now, an older robotic system would just crash because tidy up isn't a coordinate. But LEO doesn't just output a single action. It analyzes the 3D point cloud of the messy room, identifies the semantic state of the objects, like clothes on the floor, an unmade bed, and outputs a sequential logical plan.
It outputs 1, clean the floor by sweeping, 2, make the bed, 3, fold and organize the clothes.
Right. It understands the semantics of what messy means in a 3D context, likely because it can see the bounding boxes of clothes intersecting with the floor plane in a disorganized way.
And it can engage in multi-turn dialogue about that physical space. It doesn't just give a plan and shut down.
Well, the multi-turn example is great.
In one of the examples detailed in the research, the user asks for help organizing the bedroom. LEO replies, asking what specifically they need help with. The user asks, "Can you check if there are any clean clothes hanging on the wall?"
And LEO actually looks at the 3D scene.
And replies, "I'm sorry, but the clothes hanging on the wall are messy." It is grounding its conversational language in the physical state of the 3D point cloud.
And it is capable of correcting the user's false assumptions based on its own physical perception.
Yes, exactly.
And then there is the embodied the actual robotics. We discuss how they mathematically mapped arm movements and navigation steps to discrete language tokens.
Right.
They tested this on embodied navigation tasks, where the agent has to find a specific object by sequentially moving around a complex scene. And robotic manipulation tasks, like a prompt commanding it to pack the Yoshi figure in the brown box.
And LEO achieved comparable performance to state-of-the-art models that were custom-built just for those specific robotic tasks.
Which is incredible for a generalist.
What is particularly exciting about the robotics performance is LEO's zero-shot generalization capabilities.
Okay, define zero shot for us.
In machine learning, zero shot means asking the model to do something it was never explicitly trained to do, or placing it in an environment it has never seen before without giving it any additional training examples.
So no practice runs.
Zero practice runs. The researchers trained LEO on a massive data set of 3D scenes called 3R scan. Then, to test its true spatial intelligence, they tested it on an entirely different data set of scan scenes called ScanIt.
And how did it do?
LEO successfully generalized to these novel unseen scenes. The fundamental rules it learned about spatial relations, occlusion, and object physics transferred over seamlessly to new architectures.
Now I have to jump in here and pump the brakes.
Okay, hit the brakes.
I always push back when a paper presents results that sound almost too perfect. I mean, we are talking about solving spatial reasoning, mapping actions to tokens, beating specialists. What are the blind spots here?
They do exist.
Did the authors admit to anything the agent can't do yet? What are the mechanical limitations of this architecture?
The authors are actually very transparent about the limitations, which adds a lot of credibility to the research. While it did show zero-shot generalization between datasets, they acknowledge that generalizing to entirely novel scenes with radically different object distributions still remains a significant computational challenge.
So if you put it in a room that looks like nothing it has ever seen, it struggles.
Right. The model's performance drops when the physical environment is too far outside its training distribution.
And there's also a critical technical trade-off they mentioned regarding the navigation benchmarks. Something about sacrificing recurrence.
Yes, that is a crucial architectural detail. There is a notable gap between simply learning vision language concepts in a static room and actually controlling embodied actions over a long period of time in a dynamic environment.
Because things change as you move.
Exactly. When Leo navigates a room, it uses a feed-forward policy. That means the transformer architecture only looks at the current user instruction, the current visual observation, and its past 4 actions to predict the next step.
It does not have recurrence.
It does not.
So by recurrence, you mean recurrent neural networks, or LSTMs, where the model maintains an internal memory state that loops back on itself.
Exactly. Or even just a massively extended context window. Without recurrence, Leo doesn't have a deep, persistent memory loop of everything it has seen in the room so far during its navigation.
Oh, so if it walks past a kitchen island and enters the living room, it essentially forgets the layout of the kitchen island.
It does. The researchers explicitly state this was a deliberate trade-off. They sacrificed long horizon recurrence to gain training efficiency because training recurrent models on 3D point clouds is computationally punishing.
Yeah, that makes sense. So future versions of Leo will likely need more sophisticated memory architectures to navigate complex maze-like environments over long periods.
Definitely. But the paper also includes a chart that proves this limitation is temporary.
Oh, right, the scaling loss.
Yes. They tracked the test loss, which is a mathematical measure of how often the model makes prediction errors, as they systematically increase the amount of training data and the size of the neural network model.
And what happened?
The results mirror the most profound discoveries in AI over the last few years. Just like we have seen in 2D language models, the line on the graph goes steadily down and to the right.
So as the data and model scale grow, LEO's performance improves predictably, following a power law.
Yes. This is a massive finding because it proves that 3D generalist agents will keep getting smarter simply by adding more GPU compute and more spatial data.
We haven't hit an architectural wall. We have just built the first highly scalable engine for 3D understanding.
Exactly.
Which brings us to the real-world implications of all this. Because, why does a paper on 3D tokenization and spatial transformers matter to you, the listener?
Well, it matters a lot.
It matters because LEO represents a foundational step toward AI that can truly act as an autonomous agent in our physical spaces. We are talking about the back-end software for advanced augmented reality and virtual reality applications.
Imagine wearing AR glasses powered by a descendant of LEO.
Right. It doesn't just stupidly overlay a 2D text screen on your vision.
Oh.
It actively processes the 3D point cloud of your kitchen.
It knows exactly where your keys are behind the toaster because it understands physical occlusion, and it can guide you to them using spatially aware directions.
For household robotics, this architecture is a massive leap forward. A robotic assistant needs to understand its environment deeply enough to know that it cannot place a hot coffee cup on a slanted magazine.
Or that it needs to physically move a dining chair out of the way to reach a fallen object under the table.
Exactly. This unified, tokenized architecture bridges the gap between high-level human conversational language and the low-level physical control of motors and servos required to interact safely with human environments.
It connects the brain to the body.
But looking at all this, the spatial reasoning, the discretized action tokens, the ability to parse complex 3D scenes, my mind immediately went somewhere far outside of a household robot cleaning a bedroom.
Where did your mind go?
I started thinking about extreme environments. Disaster recovery.
You mean sending an autonomous, multi-agent descendant of LEO into hazardous dynamic environments?
Exactly. Now, to be clear to our listeners, we are entering our novel notions segment.
Here we go.
Yes, this is truly speculative. It is an exploration of where this technology could theoretically go, and it is for entertainment purposes only. Do not base your startup ideas or investments on my wild extrapolations.
Duly noted.
But imagine this concept. I call it the swarm spatial tokenizer.
Swarm spatial tokenizer. Okay, I am intrigued. How does it work?
We have just spent the last hour discussing how Leo takes a static 3D point cloud of a living room and maps physical 3D objects into discrete language tokens that an LLM can parse and reason about.
Right.
Well, imagine a disaster zone. A high-rise building has collapsed after a massive earthquake.
Okay, chaotic environment.
Extremely. It is far too dangerous and structurally unstable to send human rescue workers in. And standard single-agent robots get stuck because they cannot make sense of the chaotic, non-Euclidean 3D geometry of the twisted rubble.
Right. The current protocol is often flying drones in, but they stream heavy, high-bandwidth 2D video feeds back to a human operator who has to squint at a screen and guess at the physical depth and structural integrity of the debris.
Exactly. The human operator is trapped in the flatland we talked about earlier.
Yeah, that is a huge problem.
But imagine a swarm of autonomous micro-drones, a multi-agent system. They fly into the collapsed building, and instead of streaming useless 2D video, they are equipped with miniaturized LiDAR. They collectively and instantaneously build a real-time, object-centric 3D point cloud of the entire interior structure. They use a distributed edge-computed version of Leo's architecture to immediately translate that physical twisted rubble into a sequence of 3D tokens.
Oh, wow. So they are building a real-time, low-latency token map of the disaster.
Yes. They build a swarm spatial token map. Then, a central VLA model, like a massive scale-up descendant of Leo sitting securely on a server outside the blast radius, can read the physical structure of that collapsed building as easily and quickly as you or I read a novel.
Because it just reads the tokens.
Exactly. It perfectly utilizes the spatial transformer's ability to understand 3D relations to realize, load-bearing concrete beam A is resting precariously on steel rebar B.
And because it can output discretized physical actions.
Yes. It instantly generates highly precise action coordinates for heavy robotic excavators on the outside. It tells them exactly which piece of debris to pull at what precise XYZ angle to safely extract survivors without causing a secondary structural collapse.
It literally turns physical, chaotic reality into a real-time language model prompt.
Exactly.
That is a fascinating extrapolation of the architecture, because the tokenization of the 3D space, turning a massive point cloud into a sequence of vocabulary subwords, is mathematically so lightweight compared to streaming raw, uncompressed, high-definition video. The network latency would be incredibly low.
Right, because tokens are just tiny numbers.
The central agent is just processing an autoregressive sequence of tokens representing structural geometry. It takes the multimodal agent concept and applies it to critical, high-stakes structural physics.
It takes the flatland trap we started this episode with and shatters it on an industrial life-saving scale.
It really does. And on a deeper level, an architecture like this forces us to fundamentally reconsider the boundaries of what we consider to be language.
Which leads me perfectly to a final provocative thought for you to ponder long after this deep dive ends. We've built these magnificent large language models based entirely on human words, English, Mandarin, Python code. But in this research today, we saw an AI translating the physical 3D world, the geometric volume of a sofa, the spatial distance between a table and a wall, the exact physical trajectory of a robotic arm joint into language tokens for the AI to read and write.
It is its own language.
Exactly.
Yeah.
So the question is, at what point does human language become too restrictive to describe the complex spatial reasoning these agents are doing?
That is heavy.
If an AI is increasingly thinking in 3D point cloud tokens and discretized physical action vocabularies, will it eventually invent a spatial language of physics and geometry that we, stuck in our linear verbal human languages, can no longer even comprehend or translate?
That is a profound question to think about the next time you ask a text-based chatbot to solve a simple problem.
Thank you so much for joining us on this deep dive into the 3D world of embodied agents. As always, the link to the paper is in the description below if you want to explore the mathematical methodology of LEO for yourself. We will see you on the next deep dive here on Talk Tensors.